Okay, today we start working on the simplex method. So this method is used to solve the linear program just by following the special structure of a linear program or the geometric interpretation we introduced before. Okay, the idea is that to study this, we first need to recall several basic operations that can be applied to the rows of a linear system AX used to B. Okay, this is the one of the constraints we have in the linear program, okay, which is given by this. So we're looking for the vector x such that it minimizes linear objective functions subject to this linear equality constraint and also this inequality constraint, the negative inequality constraint. Okay, so we first focus on this linear linear constraint. So we need to find the x that is a solution for this linear system, and recall that there when we do certain basic row operations to this linear system, it does not change the solution x. One of these operations is the interchanging two rows. So when we switch, we have a linear system, have this A1 transpose as the first row, all the way to AM transpose as the last row. So we have this x that is equal to B, it's B1 through BM. We exchange any of these two rows. It does not, we just need to exchange the corresponding B components. Okay, but it doesn't change our solution of x. Okay, we'll multiply, that's one of them. We can also multiply by one row by a scalar. For example, we can multiply this row by 3, and it doesn't change the result either. Right? We just need to multiply the same number to this B1. So it doesn't change the solution. And we can multiply one row by some scalar and add it to another row. So for example, I multiply this row by 10 and then add it to the last row. Then we just need to multiply this number by 10 and add to the last row. And this x still doesn't change. Right? So these are the three basic operations, or the three basic row operations that can be applied to the linear system and doesn't change the solution. Okay, and each one of these three operations can be also written mathematically as a row operation matrix. And this matrix is also invertible in the sense that, for example, if I want to switch, the simplistic example is that if I want to switch a matrix A with two rows, say, but multiple columns, so it's A11, A12, A13, just for example, it could be more than 3 columns, A21, A22, A23. So you know that to switch these two rows, I can multiply this A by this vector, this matrix on the left, and then you can see I come to this E. So the E times A will become, as you can see, when I multiply this matrix to this matrix, essentially the first row is the inner product of this with that, and then with this, and then with this. And apparently this inner product gives us just a second row because I have 0, 1 here. So that first row becomes A21, A22, A23. And similarly, the last row will become the inner product of this and each of these 3 columns. And that gives us the first row, which is A11, A12, A13. So the E times A is it just switch the two rows. If we define the matrix E as this way. Okay, so the first one can be interpreted by multiplying a invertible matrix E on the left of the matrix A, and that's how we got this. Okay, and if you want to switch the i's and the jth rows of the matrix A, then your E matrix should look like this. It is modified from the identity matrix, but the ith row and the jth row, and here I also have the ith row, the jth row, I will just replace them by 0, 1, and here is 1, 0. Okay, so you move out the ones at these two locations on the diagonal and make them here, make them a 1 here. Okay, so this matrix E, when you multiply to any matrix A of the same dimension, so this E, say is M by M matrix, and you multiply to another M by N matrix, then that is just switching E times A, just switching the ith and jth rows of the matrix A. Okay, that's for the first. That's what happens when you interchange two rows. Essentially, just multiplying a matrix E like this, and you can show similar thing for the others. If you want to multiply a certain row by a non-zero scalar, then you just have this E matrix. But say, for example, you want to multiply the first row by 10, then just the first component is 10. The rest are still ones, and the others are 0. This will be your E, and when you multiply this E to the matrix A, you're just multiplying the first row of this matrix A by 10. Okay, and the third one is also simple. For example, if you want to multiply the first row by 10 and add it to the last row, then you will just have ones, and in the last row you have 1, you have 10 here. Okay, and you can easily check that. So everything else is just the ones on the diagonal and the 10 on the lower left corner. And this is essentially, if you have this as a matrix E, and you multiply this E to a matrix A, then you just keep the first m minus rows of A unchanged, and multiply the first row by 10 and add it to the last row. Okay, that is essentially what these operations can be interpreted or can be written as matrix multiplications. And all these matrices, this one, this one, this one, you can easily check they are invertible. You can easily check that they're invertible. So these three basic operations are essentially just multiplying a certain invertible matrix E on the left hand side. Okay, sorry, this should be M by M. Okay, so now you know that since we know these basic operations do not change the solution, so we can multiply them for free, and it doesn't change our solution X here. Okay, and so let's consider the original linear system AX equals to B. Then we first remember that when we, for example, we can do to solve this system, we can use Gaussian elimination. And to do that, we just combine the matrix A and the vector B into a matrix here. So this first, this is the M, has M rows and n plus 1 columns. The first n columns is just the original A. The last column is the B, right? This is called augmented matrix. And then we can apply a series of row operations to make a identity matrix, to make the first m rows as an identity matrix. Okay, and then the last column will become the solution of the system. Okay, and more specifically, what we can do here is this is the augmented matrix. We can multiply certain row operations. Say we apply T of these basic row operations, and each one of them can be one of those three operations which induced here. And then we can convert this matrix A, the first m columns of this matrix A, convert it into an identity matrix here, which is the ones on the diagonal, zeros off diagonals. All right, and since we're applying these two rows, then the remaining part of this matrix A not just the first m columns, but also n+1 columns, they will be changed. Okay, and this D is what do you have left since you have this matrix A here. So let's call it B, BD. This is my B vector. So this part here will be A. I'm writing this in this way because we're assuming that the first m columns of A are linearly independent. Because A is a non-degenerate matrix or non-singular matrix, so it must be invertible. The rank of this matrix A must be equal to the number of rows. So it must have m linearly independent columns. So we can switch the columns as we want. Just make sure that first, just without loss of generality, we assume the first m columns are linearly independent, and these columns together is called the B matrix, and they're linearly independent means that B is invertible. So if it's invertible, then I can rewrite every other columns here. So these are m columns, these are n minus m columns. I can write each of these columns here as a linear combination of the columns here, and the coefficients will be given by this D matrix. So anyway, I can rewrite this A as B and BD. So they together is n columns. There are n columns here, and this is a single column. We put the B here. Okay, so if we can do this, then we can make the basic row operations. Apply the basic row operations. Then I will convert this B into a diagonal matrix, and these row operations together is just the inverse of B. Okay, so so the D, so this all together will be the B inverse, and the D is just what happens when we apply the B inverse here. As you can see, together with this B, they will become identity, and when you multiply B inverse to this part, then you just get the D. Okay, so D is essentially just the coefficients we need to use to represent the last n minus m columns of A using the first m columns of A. Okay, so that is the matrix A. So we introduce the B and D here just to make things more clear. Okay, so if we can apply this B inverse here, we get the original augmented system, augmented matrix becomes this. Right? Because this first one is B inverse times B, that's just identity. The B inverse times BD, that's just D here. And the B inverse times the vector B, that will be this. Okay, and then we can get a solution for the linear system very easily. The system is just this. Right? This is what something we have seen before. So when you multiply the A to this, it will be equal to B. The reason is now the AX, which becomes the BD times X, where X is this B inverse B and 0 here. And when we multiply the B inverse on both sides of AX, it will be B inverse B. So this is equivalent to AX equals to B, right? So now what I'm showing is that the AX on the left-hand side is just this, right? So when I multiply both sides, so on the right-hand side, I will just have the B vector. So if I multiply both sides by B inverse, I will get the B inverse times BD and the B inverse B and 0. And as you can see, I will just get identity and D. And I have B inverse times B and 0. And when I multiply these two together, we'll just get the B inverse B. And that is exactly the right-hand side. Right? It will be exactly the right-hand side here. Okay, so the left-hand side becomes this, and the right-hand side is the same as the right-hand side. And we know that for this X, for this choice of X, it satisfies this, or equivalently satisfies this. Okay, so that's a particular solution. Okay, but you know that when this matrix A is a fat and short, the matrix A looks like this, has m rows and n columns. It's my matrix A. And when I multiply vector B vex, I get a B vector. There are multiple solutions coming from this. There are actually infinitely many solutions for that can satisfy this linear system AX equals to B. So this A, this X, and this is B. But what is a general solution for that? What we found earlier is a particular solution. It's just one of those infinitely many solutions. But every solution of this system can be written as a general solution, can be written as a particular solution plus the representation of the general solution of AX equals to 0, right? So what I'm trying to say here is solution to AX equals to B can be written as X star is a solution of AX equals to B if and only if X star can be written as a particular solution X. Let me call it X hat here, plus some X tilde, where X tilde makes AX equals to 0. AX tilde equals to 0. Okay, so the X tilde can be any one of this. Okay, it can be from this set. And X hat here is a specific solution. It's a particular solution. But this X tilde is a general solution of this homogeneous linear system. Okay, so any solution of this can be written as the sum of a particular solution plus a general solution of the homogeneous system like this. The question is, how many choices I have here, or what is the dimension of this one? This is also called, I believe it, if taken the linear algebra class, this is called the null space of the matrix A. Okay, it's all the vectors such that when multiplied by A from left, you get 0 vector. And the dimension of this null space is equal to, I hope you remember the dimension of the null space is what? If this matrix A is M by N, and then the null space essentially is just the vectors, the space of vectors, which are perpendicular to every row of this matrix A. So when you multiply this A matrix to this vector X, you get 0, just the zeros here. So what this means is that X tilde is in the null space, right? And what kind of X tilde can make this right hand side equal to 0? Can make this product as 0? It is if and only if this X tilde vector is perpendicular to every row here. Okay, every row here. And remember, there are m rows, and since the rank of A is m, so that means these m rows are linearly independent. So they can form a m-dimensional linear subspace of Rn, and the subspace has a dimension m. So the space that is perpendicular to this subspace will have a dimension n minus m. So that means this null space has dimension n minus m. Okay? Or in other words, you can find a basis with n minus m vectors. They are linearly independent, and they can span the whole space, whole null space. Okay, so that is a general solution for the homogeneous linear system. And the general solution for the inhomogeneous system here is just to be written as a particular solution plus that. Right? That's what you learn in linear algebra. And now let's go back to the linear system here. Since we found a particular solution, and then we also know a general solution for the homogeneous system AX equals 0, because AX equals 0, when I multiply the B inverse on the both sides, I will get I times, so the AX equals to B is the same as the BD times X equals to 0. right? And then when I multiply the B inverse on both sides, I will have just the identity and the D times X, which is equal to 0. Okay, in the for this one to be 0, the X can be any one of this. Okay, XD is arbitrary n minus m dimensional vector, arbitrary n minus m dimensional vector like this, and we just need to multiply this vector by the negative d, then this will make this equality hold. Okay, so we can verify that easily. So if the first m components are of this x are negative dxd, the last n minus m components is the xd here. Then when we multiply these two together, I'll get negative dxd, and then d times xd, which is d times xd, and that gives us 0. All right, so that means for any vector n minus m dimensional vector xt here, I can construct this vector x, and they will become a solution of the homogeneous system, homogeneous linear system. And that means this solution will be inside this space. Okay, will be inside the null space. Okay, now let's see what are the how many choices I can have here. We said that this xt can be free, right? Can be any vector in this space. So that means the dimension of this will be at least n minus m. Okay, so that means consider the space formed by these xd's. So let's say this negative dxd and xd, which is n-dimensional vector, and the xd can be arbitrary n minus m dimensional vector. And then we compare. We said that every one of this will be inside here. So that means this is a subset of this set. Okay, but on the other side, we know that this one has a dimension n minus m. It's a linear space subspace and has dimension n minus m. And this is a linear subspace of Rn as well. And the dimension of this is also n minus m, because the xd can be chosen freely as any n minus m dimensional vector. So that means these two sets are actually equal. Okay, any vector x tilde can be written as this way. All right, so that means we know the particular solution. We already found a particular solution, which is this. And we also found a general solution for the homogeneous system. So we can just add them up to form the general solution of the inhomogeneous system here. So this is the presentation below. X can be written as the sum of a particular solution plus a general solution for the homogeneous system. Okay, so any solution to ax equals to b can be written in this way. And this xd is arbitrary n minus m dimensional vector. Okay, so now with this as the foundations, we can consider applying basic row operations and convert this ax equals to b linear system into this form. Okay, so this y is nothing but the d earlier, but the vector d earlier, and this y0 is the b inverse times the vector b as before. Okay, we write it in this way because we're going to use these y's in the derivation of the simplex method. Okay, so as we mentioned earlier, this y is the d vector, and is a d matrix, and this d matrix is the coefficients we use to represent the last n minus m columns of A using the first m columns of A. Okay, so that's the meaning of this y. Okay, and the y here has m rows, as you can see, m rows, and n minus m columns. Okay, because we have n minus m columns remaining after we take out the first m columns. And this y0 is, as we said, this is just a, this is the b inverse times b. And this y is the previously is called the d. Okay. And this is just repeating what I just said. This the qth column. So for example, this column, the m plus 1 column here. This is just the coefficients we use to represent the am plus 1, the column am plus 1, by the first m columns a1 through am. Okay, and generally speaking, for the q's column here, we have the yq, and the q is bigger than m. So it starts from m plus 1, and then m plus 2 all the way to n. So the yq here is composed of the scalars, or the coefficients that we use to represent aq. This is the q's column of the original matrix A, using the first m columns of the matrix A. So we use the y1q for the a1, y2q for a2, up to ymq for the am. Okay, and so this aq is nothing but this. So in other words, the aq is just the product or the multiplication of the matrix, the first composed of the first m columns of the matrix A, and this yq, which is the q's column here, the q's column here. Okay, so that's why, as we said, y is just a matrix of coefficients, and that's why this is because A is written as b and by. Okay, and so now let's say that if we use a1 through am as the basic columns, and this x, recall the basic column is the columns we use to represent the vector b. Okay, they are the basic columns. And the x here is defined as this b inverse b and 0. So this will be the coefficients we use to represent the vector b. Okay, and we know that this will give us the a basic solution ax equals to b. Okay, the reason is here that, as we said, you already converted the ax equals to b is the same as the by x equals to b. When I multiply the b inverse on both sides, it will become yx equals to b inverse b. Okay, so as you can see that when we substitute the x by this, as we did before, we'll just get that right hand side. So this x is a basic solution. The first m columns of the matrix A are basic columns. And say if we already have this x as, if this vector x is already greater than or equal to 0, non-negative, or in other words, this part is non-negative since it's already 0, then this x is already a basic feasible point, right? Because it, on one side, it satisfies ax equals to b, and is greater than or equal to 0. On the other hand, we know that this is a basic solution because there are the n minus m components here are zeros, and we can have at the most m non-zero components in x, so that's why x is also basic. Okay, so if b inverse times b is non-negative, or this part is non-negative, then this x will be a basic feasible point of the linear program. All right, and that also means that we already reached to one of the vertices of the polyhedra described by the equality and inequality constraints. Or in other words, go back to the picture we showed before, if our b inverse times b is already greater than or equal to 0, then that means we must be at one of those vertices already. Then we can continue doing that. We can continue following the path to get to the next basic feasible point and check the function value, and eventually we reach to the point where the function value cannot be further decreased, and that is where the optimal solution is. Okay, so here what it says is just that we check these and see if this is greater than or equal to 0. If it is, then we're already at one of the vertices. Okay, so from now on, we temporarily assume that we already reached to a basic feasible point. Means that we already reached to some solution like this, where this is greater than or equal to 0. And this is we're assuming that we're already at one of the vertices. And then we consider how to move to the next basic solution, or to the next vertex. And later on, we're going to show that how we're going to find the first basic feasible point. Okay, so as we said, we temporarily assume that we're already at a basic feasible point. We're trying to move to another basic feasible point, or another vertex of the polyhedra. Okay, so to move to another basic feasible point, we're going to change our choice of basic columns, because a basic feasible point corresponds to the basic columns. They're using certain columns of the matrix A to form the vector B. Okay, if you're going to change your basic feasible point, essentially you're just going to choose another set of basic columns. We're not going to change all of them altogether, but we're just going to change one of them. So that means originally the matrix A has this A1 through AM as the basic columns, and then have M plus 1 all the way to AN. This is my matrix A. Originally, we select this M columns as the basic columns. But now, I'm going to delete one of them, so remove one of them, and replace it by one of the others. And then we'll get a new set of basic columns, and then we have the corresponding basic feasible point, and that is a new vertex of the polyhedral. And then we check if the function value is, we want to move to this point such that the function value decreases. Okay, so there will be, as you can see that the question is how do we replace one of these basic columns by one of the columns here. Suppose we decide to exchange the pth column, say pth column is one of these columns, by the qth column here. Q is one of these columns here. Okay? If we decided to go for like that, then we are essentially just changing the current matrix, which is modified into this form. We will change one of these columns in this I. So remember that currently this A is already multiplied by the B inverse. The B inverse times A will be already a 1s here, and then we'll have the y1 m plus 1 all the way to ym m plus 1 to the last one, which is y1n, and then ymn. So if we're going to replace one of these columns by one of these columns, for example, the last one, then I would just need to make a basic row operations such that this column becomes just the corresponding ones. So let's say, for example, I want to replace the first column here by the last column here. And what I need to do is to apply basic row operations such that this last column becomes 1, 0, 0, 0. Okay, and it will only change the first column here, because when I do row operations, I add this I make these kind of operations to cancel the rest, and also modify this first one to 1. What I will change is only this column here. Okay, the other columns will not change because the other column only has 1 here. It will not be touched. Okay, so that's you know that this is true when you do the Gaussian elimination. You know that we do operations on this to make this become 1, 0, 0, 0. Then eventually what you get is this will be just some non-zero numbers, and this part will be unchanged, and this will be always they will be all changed, including the last column. But last column purpose that last column is changed to 1, 0, 0, 0. This factor. Okay, so that's the case when we exchange, when we want to replace the first column by the last column to form the new basic columns. So now after you change that, the basic columns will be from the second column here to the mth column here plus the last column. There will be still m columns, and there will be the new set of basic columns. Okay, so this is how we're going to exchange the pth column and the qth column here. We replace, exchange them. So the question now becomes which column we should pick to delete, and which column we should pick here to replace it, to replace the deleted one. Okay, so these two questions are the key that we need to answer. Okay. So now let's see which one we should which one should delete and which one should replace. So first recall that the the vector x, the solution x, is essentially just the basic feasible point that we already have right now. It's a basic solution, and it solves this x to b. So that means when I multiply a to this vector, I will get b. So when I multiply this a to this vector, which is this, so this is just like the column vector with this as the components. And you can see that it's just making a linear combination of the first m columns of the matrix A. Okay, and the coefficients are given by these numbers. So the y10 is coefficient for the vector a1, the first column of A, up to the mth column of A. It's multiplied by this, and this all together gives me the b vector. Okay, now suppose we decide to replace one of these basic columns by the AQ, and then recall that AQ can be written as a linear combinations of A1 through AM, and using the y q as the coefficients. Remember that this yq is this q column in this big matrix Y, right? So the yq is just that. So this will be the coefficient that we use to represent AQ using the A1 through AM. All right. Now recall that because this is equal to B, and the same thing here equals to the same vectors but different combination coefficients give us the AQ. So I can subtract these two equations. Then essentially I'll just subtract epsilon times this equation from the first equation. So what we'll get is this minus epsilon times this, and then we'll have the second coefficient will minus the epsilon times the second coefficient, all the way to the last one, this one minus epsilon times this one, and that will keep the vectors unchanged. That will be this. At the same time, this AQ can be moved to the right. It will become 0. This side I'll have AQ, and this side is multiplied by epsilon, and I subtract it from this one. I'll get this epsilon AQ. Okay, so this is just multiply the second row by epsilon and subtract it from the first row, first equation. Then I'll get this. I'll get this. Okay, so now you can see if I decide to use AQ as one of the new basic columns, and what I can essentially do is just to choose a proper epsilon so that this one of these m numbers becomes 0. And then this AQ will be the new way to form the vector B. Okay, so it will become the new basic columns. So that question only becomes which one will become 0 first, right? We should set epsilon to 0 and then gradually increase it until one of these m numbers becomes 0. And apparently, the smallest epsilon we can find will make this one become 0. So the epsilon should be chosen as this component-wise division. So what I'm saying is that for this one to be 0, this is similar as before. For this one to be 0, epsilon needs to be equal to this divided by this. Okay, the second term is similar, and up to the last term, for this last term to become 0, the epsilon needs to be this divided by this. Okay, so the first component will be just the y0, right? Just the first, second up to the mth component of y0. And then this is just the components of the vector yq. So you can think this as a component-wise division of y0, this is the vector, by this yq vector. This is component-wise division, so I will still get the m-dimensional vector. And we just look for the minimum value and see which one is the smallest. And then that will be my epsilon. By choosing that epsilon, I can make sure that this one of this becomes 0. Okay, or the corresponding one. If I choose epsilon to be that one, then the one of this will become 0. Okay, as we said, by taking the component-wise division of these two vectors, we'll get a new vector, and just choose the smallest positive number of this vector. That will be our epsilon. And this epsilon, when we plug this into this equation here, then we'll get one of these coefficients 0. And then we introduce the AQ as a new basic column and remove that, the one that with the 0 as the coefficient, remove that column from the original set of basic columns. Okay, so now, so this is just repeating what I just mentioned. Look at the yq's, and then we take the component-wise division of y0 and yq, and then check the smallest value. Oh, by the way, I think I didn't mention, but you probably have realized that when I write it out, or write a vector out, I have to use, I need to use the vector notation. But for this slide, if it's bold-faced, lowercase bold-faced letter, that means it's a vector. If it's just a standard lowercase letters without the bold-face, that means it's a scalar. Okay, and if it's uppercase with a bold-face, that means a matrix. Okay, just in case you haven't realized that. All right, so as I mentioned, we just check the values of this and find out what the minimum value, and then say suppose the p's column, the p's column a p has this. Also, the epsilon corresponds to yp0 over ypq. In that case, the coefficient in front of a p will become 0 first. So the pth, there is a p here, and the coefficient of that will become 0 by choosing that specific epsilon, by choosing this epsilon. Then in this case, we're going to remove the AP from the original set of basic columns and replace it by the AQ vector. Okay, so this notation means that it's A1 through AM, but we have the hat on top of AP means that this one is removed, and the AQ will be replacing the original AQ. Okay, so now we consider. So this is how we how we're going to decide which AP is to be removed. And next, we're going to consider which vector AQ is going to enter. Right? So we're going to the reason why we're going to replace the AP by the AQ is because if we use the AQ as a basic column, then the corresponding basic solution has a smaller function value. Or in other words, if we choose AQ as a new basic column, then we're moving from one vertex, we had it at the beginning of this iteration, to the next vertex, and then we hope to move to the vertex that has a smaller function value. Right? So that's the purpose. So the AQ should be chosen by keeping this in mind. Okay, so now let's see how this AQ, what kind of AQ which AQ we should choose to decrease the function value. Okay, suppose at this moment our basic point is this x is the y not 0. And now if we choose a q to enter the set of basic columns, then let's see what is the new objective function we will get. Remember that the if I look closer into this equation, what I will really get is this is a this will be A matrix times this will be the y0 part. This is the first m components of the x, right? This will be this part, which is here. Okay, and then the others are zeros. So this is the basic solution that I'm having at this moment. This is the x vector, right? And this I know that is equal to b. And on the other hand, I know that when I multiply a by this q vector, so that when I multiply a, sorry, it's not a vector, by yq, and all the others are 0. By multiplying a by this vector, I know this is equal to baq, right? I'm going to move this aq to the left. I'll get 0 vector. All right, so this equation right here is nothing but multiplying this one by epsilon, then subtract from this one. So what I really get is a times this vector y hat, y vector, y0 vector, and then 0. So I just write them all those multiple zeros into 1, because this part, this part is the the first m components. The rest will be n minus m components. Okay, so this 0 here denotes the remaining n minus m zeros, minus epsilon times this first vector. So let me continue writing this. So this is the a times y0, yq, 0, 0, 0, minus, remember that the aq is just the qth column of the matrix A. So it's like I'm multiplying a, so it's not a vector. I'm multiplying a by this vector, which is 0, 0, 0, and then 0. One of them is 1, and this is the qth one. Right? Because when I multiply a by this vector, I will just end up with the q's column of the matrix A. Okay, just the 1 as the q's component in this vector, and all the other components as 0. So this is equal to, as we said, it's equal to 0 vector. So as we said, if I subtract this by epsilon times this, then on the left hand side I will have a minus a times this vector minus epsilon times the difference of these two vectors is yq, 0, and this vector I denoted by this vector. I'm going to denote it by eq. eq is just the n-dimensional vector with the q's component as 0, as 1, the other components as 0. I'm just having this as the eq. Right? So OA is multiplied to this difference, and that on the right hand side I have the b vector. Okay, so that's the this will give us the new basic solution. This whole thing will be the new basic solution. Okay, this will be my new y. So to check the function value of this new vector, I just need to multiply the vector c to it, make an inner product of the c and this vector. Okay, so let's see what happens. So as I just mentioned, I can merge these two. I can merge these two first. Now I will only get, say I write it on the top, the vector becomes the y0 minus epsilon yq. Remember that these two y vectors are both m-dimensional vectors. And then I still have the 0 vector. And then I also add the epsilon times eq. eq is a n-dimensional vector. Okay, so both are n-dimensional vectors. So I need to multiply the cost c, cost vector c, or the c vector to this. That will be my new function value. Okay, that's essentially what this one is. What this one is. Okay, it's the same one. Okay, so now let's just multiply them together. Apparently, when I multiply this c vector and this vector, I know that only the first m components are making difference, because the rest of them, the rest part of the c will be multiplied to 0, and then just giving me 0. Right? So essentially, these two multiplied together is just the first m components times this. So that would be the equivalent to, let's see, transpose y0 minus epsilon yq 0. It's the same as the vector c1 through cm. So these are just the first m components of c times this y0 minus epsilon yq. Sorry, just this self. Don't have this 0 anymore. Okay, this is my vector. So I gave a notation here. The zi denotes the inner product of yi and the vector formed by the first m components of c. So this c1 through m is like a MATLAB notation, just the first components of the vector c, and multiply inner product of this vector and the yi, because y is an m-dimensional vector as well. Okay, and from that you can see that when I multiply this and the y0, I'm just getting z0 or z0 according to my notation here. And also multiply this and the yq, then I get zq as I defined for the z. So this is equal to the z0, which is scalar, the inner product of the two vectors, minus epsilon zq. Okay, they're all scalars. So that's for the inner product of these two, right? And I also have the inner product of the c and this epsilon eq. So epsilon is a constant, I can move it out. The c times eq, because the eq only has one component, the qth component is 1, or the other is 0. So the product of these two is just nothing but the qth component of c. That is a scalar as well. So when I multiply these two together, I will get just cq. So when I put everything together, I will get, so as I said, these two together gives me this z0 minus epsilon zq. And these two together gives me epsilon cq. Okay, and all together they just become this. Okay, z0 plus epsilon times cq minus zq. All right. So that's what the new function value is. When we move from this original feasible, basic feasible point to the new basic feasible point, this will be the new function value. So recall that this is the original function, original point. When I multiply this by c transpose times x, I will just get z0. So that means that z0 is the objective function value at this point. And this epsilon is greater than or equal to 0, as we said. So if I want to further decrease the function value, I just need to make sure that CQ minus ZQ is negative. Okay, CQ cannot change it, just the Q's component, and that all depends on what this ZQ is. Okay, so we're going to. So now we can see that for each of the vectors that are not basic columns right now, we have a CQ minus ZQ, and we just need to look for the Q such that this is the smallest, it's the most negative one. And in that case, we're going to decrease the function value fastest. Okay, so this is what I said. If CQ minus ZQ is smaller than 0, it's negative for some Q, then by choosing that corresponding Q, so for example, Cn minus Gn is a negative number, then by choosing An as a new basic column, we will potentially get smaller function value because this is negative, this is positive, so Z0 minus plus this number will be a smaller number than Z0 itself. So we're going to decrease the function value. So once this is negative, we can let AQ enter the set of basic columns and replace the AP by this AQ. And we can further decrease the function value. If there are multiple negative values here, we just choose the Q that is the most negative one. Okay, just to have the smallest value, CQ minus ZQ. If all of these values are positive, okay, in contrary to this, which is negative for some Q, the opposite is that all of these are greater than or equal to 0 for all Q. And in this case, that means it doesn't matter which AQ we're going to choose, the objective function value here, the new objective function value here is greater than or equal to Z0. That means we cannot further decrease the function value. Then that means we already found the optimal feasible basic feasible point. All right, so that is the logic here. So now we answer two things. One thing at the beginning is that if we decided a Q to enter to be a new basic column, and we're going to replace one of the old basic columns, then this tells us which one we should replace. Okay, and that depends on if we know the AQ, then just to make this division for different P's, and we see which one is the smallest one, then we're going to remove that corresponding AP, right? And these slides shows that which vector Q we should use as a new column vector, new basic column, and that based on for the remaining remaining vectors, we check AQ minus ZQ. The most negative one will become the AQ, will be the AQ that enters the set of basic columns. If none of these are negative, then we can stop. Okay, so this is the procedure of the simplex method. It's a bit complicated because of we need to decide which vector to remove, which basic column to remove from the set of basic columns, and which vector or which column of the A to enter. Okay, all this procedure can be summarized in a very elegant and nice way using a matrix form. Okay, this is what we're going to talk about next. By the way, we're assuming that we started from, as we said earlier, we are assuming that we started from a basic feasible point, and that and as I said, we are going to discuss how do we find this first basic feasible point later on. But right now, assuming that we already have a basic feasible point, then we should proceed with that, and to find the optimal basic feasible point. Okay, and this matrix form I just mentioned for this part is called the it's called the tableau. Okay, so what this one is recall that the standard form of a linear program is written in this way, right? And now the tableau of this linear program is to see that is to extract the parameters of this problem, which are the matrix A, the vector B, and this vector C. and I'm going to put them in this way. So the matrix A is upper left corner of this matrix, B of this tableau. The B is the vector. So this first block here is just the augmented matrix of this linear system. And then I will put this C as a row vector below this matrix A, and put a 0 scalar as the last entry. Okay, so this matrix, as you can see, it has this A has m rows and columns, and then we have one more column here, so it's n plus 1 columns. And then we put a row vector below A, so this has m plus 1 rows. So that's the size of this. That's the size of this tablet. Okay, and also recall that we can separate our partitions A into two groups. One group is the first m columns, we call it B, and we call the last m columns D. We used to have B times D or B times Y, but right now I just say that the rest, the remaining columns of A will be called D here, and also we can separate this C vector into CB and CD just to decide which part is below which matrix. So now the B is m by m square matrix. D is m by n minus m rectangle matrix, potentially rectangle matrix. And this will be m dimensional vector, n minus m dimensional vector. And as you can see, this tableau contains all the information from the linear program, because in the linear program, these A, B, and C are the only parameters. Only problem parameters. Okay, we're supposed to get the x using this A, B, and C. Okay, so now recall that we can do for this tableau or for this matrix here. If we multiply this matrix on the left, then what happens is this is essentially the same as we're doing the B inverse, multiply the B inverse into the matrix A and B, or get the canonical form, as we mentioned earlier. So let's say that we just put this matrix in front of the tableau, and then as you can see, this is the block diagonal matrix. When multiplied to this matrix, I'm essentially just multiplying this block to each one of the top row. There's 1 to each one of the bottom row. Okay, and then notice that this is the m plus 1 by m plus 1 matrix. This is the m by m upper leading principal submatrix. This is the last entry here. So when you multiply them together, as I mentioned, just multiply this to each of this, and you get these two together gives you the identity matrix. This gives us the B inverse times D, and then this B inverse times this vector B gives us this basic variables. And the bottom row gives us the CB, CD 0 because it's just 1, it doesn't change anything. And now, once we get this, we can see something familiar with, right? This identity matrix we saw earlier. This is the coefficients that we use to represent the last n columns, last n minus m columns of the matrix A by the first m columns of the matrix A. And this B inverse times B is the basic variable. Okay, so this thing will be the non-zero, the potentially non-zero part of the basic solution. Okay, so we can further multiply this matrix, identity 1 and negative B transpose. We will multiply this matrix to this matrix. Then what do we get? So this is just a multiplication of the two. What do we get? The identity, again, this is the block matrix. I multiply the first, when I multiply this first block, first row to this, I will not change anything, right? Because it would just keep the first row. But when I multiply this row and this column, this and this, and then this is this, what I get is apparently this times I plus 1 times this gives us 0, and then this times this plus 1 times CD gives us this, and this times this plus this times 0 gives us this. Okay, so what this actually is, that goes back to the derivation we had earlier, which is lengthy derivations we had, because this summarized the procedure we did earlier. Let's check. First of all, this B inverse B is the basic variables, okay, and we just pad them by 0, we'll get the basic solution. So that's this. Second is that this part, recall that what we're trying to get is this, we were trying to evaluate the CQ minus ZQ and see which one is the most negative one. So the CQ minus ZQ is just the components of this vector. This is the component of this vector because the CQ, Q is from n plus 1 to n. So there's all these CQs are contained in this CD vector, right? Because the C vector, if I put at 0 vector, then I have the C1 all the way to C M, and then we have the Cm plus 1. Maybe I have the CQ in between, and then Cn. Okay, and then this part is called the CB vector, and this part is called the CD vector. So I need to check the difference between CQ and the ZQ. So CQs are all here, right? This one all the way to this one to this one. So all the CQs will be here, and the CB transpose B inverse D. What this term is. So first of all, as we said, B inverse times D is the Y vector we showed earlier. These are the coefficients we use to represent the last n minus m columns of A using the first m columns. Right? That will be our Y. And then we multiply by the CB. That is exactly the Z we mentioned, because the Z is just this vector. That is the CB vector we mentioned. Right? Because this is the CB vector. This is also equal to the C of 1 through m. Okay, first m components of C. And now, how about this one? The Yi is the ith column of the B inverse D. Okay, so this one is the ith column of B inverse times D. So if I'm interested in the Y, the ZQ, then I'm just multiplying the CB vector with the Q column of this matrix. But this matrix, the first column is the m plus 1th column, okay, up to the nth column. Okay, so that's exactly what this term is. Okay, so that's this is the vector. This is the vector here where the qth one is CQ minus the CB transpose. This CB is a vector because the component is composed of the first m columns times the first m components of the vector C. And then B inverse D is the Y's. So this will be the Y1, Ym plus 1 through Yn. Sorry, this should be just the YQ. Q is one of them. Should be just the YQ. Okay, so that's the Q's one. The Q is from m plus 1 to n. Okay, so essentially this vector here is a n minus m dimensional row vector, and that is composed of the components like this. And this is the one that we're going to check the value, right? The most negative value will be the factor that will determine the new vector AQ to enter the basic columns. And this last one here is the current objective function value, because this is just the y0 part, the y0 vector. And we'll multiply CB and this y0 part, I will get the z0 as we showed earlier. Right, this part here will be just the z0. Okay, the scalar. And the negative, I put negative here, but actually the z0 itself is the optimal objective function value. It's the objective function value when we have this as a basic variable, a basic solution. Okay, so it's the goal is to further decrease this value, and how to decrease is that we're going to select. So these are the original basic columns. We're going to select one of these ones to be a new basic column, and exchange one of these columns with one of these columns, and then we're going to essentially change the value here and also here. And how do we decide which one to replace? We're going to look at those values. The most negative values will be the one we used as the new basic vector. Okay. So that's the summarizing what I just said. This is the basic variable as we saw in this modified tableau. This is the basic variable. This is the values we are going to check which one is the most negative one, and that corresponding AQ will be the new basic column. And this is the current objective function without negative. It's the current objective function value. And to determine which of the original basic column to replace, we're going to check the corresponding values here and the Q's column in this matrix. So that's the thing that we're going to discuss next. Okay, to summarize what we discussed earlier, the simplex method should work in the following order. In each iteration, we should check the tableau. We should check the tableau here and see that we look at the last row of this tableau, and we're going to find a bunch of numbers and look for the most negative number. This is the non-zero, potentially non-zero values in the last column, in the last row of the tableau, right? And we're going to look for the most negative component from this vector and say that's the qth one, and this will be the corresponding AQ will be a new basic column to enter. And once we decided that Q, and we're going to look at the vector above this Q vector. So for example, I have the AQ. So this vector, this row vector is just this one. Say this one has the most negative value. Then just look at the column above it. Just look at the column above it, or there's a column above it. This is the Q's one. Then I will check, we'll divide this column. We'll divide this column by here. This is like corresponding to the Y0. And this one is the YQ. So I'm going to divide these two columns component-wise. So that's the Y0 divided by YQ I mentioned earlier. Do this component-wise division. And then I look for the smallest positive value. And that value will be corresponding to the AP vector. And that AP vector will exit the set of basic columns. And it will be replaced by this AQ here, the Q we chose earlier. Okay, so that's this step. Find the P such that the Y0, YI0 divided by YIQ is the smallest for a positive AQ. Okay, so this make sure that we choose, this is essentially just choosing the minimum value here is the epsilon that we choose, and the argument means that which index is the minimum, we reach the minimum. So we found this P, we found this Q first, and then find this P afterwards. Then we're going to pivot the tableau here So remember that the p's column here has the one as one components, the others are 0. And now we're going to pick up the q's one here as the new basic column. So I'm going to replace the unit vector here by this q's vector here. So I'm going to make a basic row operations so that this column here becomes that column here, because the 0, 1, 0 vector earlier. Okay, so just pivoting, by pivoting, it's just the same as we do the pivoting for row for basic row operations. So in this case, for the qth column, only the PQ entry is 1. The other entries of that qth column will become 0. Okay, after we do the pivoting. And finally, after we do this, we'll get a new tableau, and then this is the last column, but only look at the first m components. Remember this m this is a MATLAB notation denoting the last column, the first m components of the last column. Okay, and that is giving us the current basic solution, the new basic solution. And this is again the MATLAB notation. It tells this gives us the first n components of the last row of the tableau. Okay, so last row, look at the first components. Actually, there are only n plus 1 components. The first n components give us the new caustic coefficients, the C coefficients. And the last entry of this tableau is the negative of the projective function value, okay, as we showed earlier. So what I'm saying is that this new one here will be the new basic solution. This vector here is the new C, and this part without the negative will be the current function value.